Hello everyone, welcome to the third lecture on the topic of dielectrics. In this lecture, I am going to talk about internal field in dielectrics and an expression or an equation or a relation called as Clausius-Mossotti Relation. So first, let's understand what is the meaning of internal field. So usually in gases, we know that the distance between atoms is very large. There is a huge separation between the different atoms. So suppose if I apply an electric field to a gaseous substance. Okay, I apply an electric field to a gaseous substance. So then a particular atom within the gaseous substance will feel the applied electric field only. There is no contribution from the neighboring atoms because all of them are maintaining social distance. All of them are staying far away. But in the case of solids and liquids, we know that atoms are placed very closely. So because of that, if I apply an electric field, then the resultant electric field acting at a particular atom, acting at any one atom, will be the sum of the applied field and the electric field created by neighboring atoms. This is what is understood as internal field in the case of solids. In the case of if it was a gaseous substance, then we have the internal field being represented by that being experienced by the atom only. It will be the same as the applied field. But when we come to solids, the internal field at an atom will be a sum of applied field and the field created by neighboring atoms. So now we are going to derive an expression for internal field in the case of solids. So for that, first let's consider a parallel plate capacitor to which a potential is being applied. And when the potential is applied, we do get free charges on the plates. Now, within the parallel plate capacitor, there is a dielectric material kept. So, when the dielectric material is kept, induced charges are formed or bound charges are being formed here at the ends of the dielectric. That means polarization occurs. Now, in addition, what I am going to do is I am going to consider an atom A at the center of this dielectric. So we have an atom at the center of this dielectric. Okay. So when this applied voltage results into an applied electric field over here, that will be acting over the atom at the center also. There will be an electric field nearby the atom at the center. So we are going to find out what is the total electric field experienced or what is the total internal field experienced in this particular setup. So we have considered a spherical cavity with a particular radius and the atom is at the center of that spherical cavity. So we will get bound charges here at the edges of the spherical cavity also. Now the internal field is going to be a sum of four components. The first one is due to the free charges. So I have designated it as E1. So E1 is the field intensity acting at that atom. Field intensity acting at that atom due to the free charges. So that is given by this particular expression. E1 is D divided by epsilon naught. Well, what was D? So D we already discussed in the first lecture, that is the electric displacement vector. But we also know that D is equal to epsilon naught into E plus P, which is the three-field vector relation. So if I apply this three-field vector relation into this first equation, it becomes E1 is equal to epsilon naught E plus P divided by epsilon naught That simplifies to E plus P by epsilon naught, where E is the applied field, P is the polarization vector, epsilon naught is the permittivity of free space. So this is the field due to the free charges on the plates, E plus P by epsilon naught. Now next comes the field due to the dielectrics. Because of the dielectric, because of the polarization happening in the dielectric, we do have the bound charges. Now that is given by minus P divided by epsilon naught. It's minus P divided by epsilon naught. I leave up to you to think why it is minus P by epsilon naught. The previous expression for E1 does give you a hint to know why it is minus P divided by epsilon naught. Those who got the answer, I request you to leave the comment and tell me what it is. Okay, and next we have another field E3, which is due to the neighboring atoms, due to many number of neighboring atoms. So we are going to consider a cubic solid. So the field due to the neighboring atoms will be very negligible. So I am going to consider it as 0. So we have got three components now. First one due to free charges. First electric field due to free charges E1. Next is electric field due to the bound charges at the sides of the dielectrics, that is E2. Next is the field due to the neighboring atoms, that is negligible, so it becomes 0. Next we are going to consider the charges on the surface of the spherical cavity. That means these positive and negative charges which you are seeing at this edges of the spherical cavity, where the center of the sphere is the atom A. So what I am going to do is, I have now expanded that spherical cavity. So this was our atom A and these are our charges, positive and negative charges. And this red line from A to Q is actually representing the radius of the sphere. So that's the radius of the sphere. So I am going to consider a small elemental area dA over here. So small elemental area between Q and R, and termed it as dA, and the angle made by that elemental area is d theta, small angle d theta. Now what we are going to do next is, we are going to consider the charge at this elemental area and then integrate throughout the sphere to find out the value of the electric field acted upon by these charges, these polarized charges over here at the spherical cavity. So first I find it at a small elemental area and then I integrate it throughout the sphere. So in order to do that, we need to learn something called as spherical polar coordinate system. So until now you have been aware of the Cartesian coordinate system, that's corresponding to the different axes x, y, z in 3 dimensions. We are going to introduce something different here. Hopefully you will be learning this in your mathematics courses at higher semesters. So we have first considered 3 axes in Cartesian coordinates, that's x-axis, y-axis and z-axis, and the origin O is over here, and with respect to the origin as a center I am going to consider a sphere. Now I can represent any point P here by 3 coordinates. I have taken this point P and I am going to represent it by 3 different coordinates. First one is this radial variable r, basically the distance O to P. Distance OP, distance to the point P from the origin, that's the radial variable or the radius r. Next, the angle made by this OP, distance OP, with respect to the z-axis, that's going to be taken as theta, or it's also called as polar angle. It's called as polar angle. Next, what we are going to do is, from this point P, I draw a projection to the plane XY. I draw a perpendicular line to the plane XY, and from O, from the origin, I connect it to this perpendicular in the plane XY. So angle made by x-axis with respect to this projection on the plane XY is given as the azimuthal angle phi. So this azimuthal angle phi varies from 0 to 360 degrees, or in radians I will say it as 0 to 2 pi. Whereas our polar angle varies from 0 to pi by 2. This you can understand very simply by assuming that Earth is like a sphere, and you can consider this origin as the center of the equator. Any position on, say, suppose this is the northern hemisphere, so let's even consider Bengaluru over here. So the position here P, the distance from the origin to the position here is the radial variable. The angle made by this distance with respect to the north pole. So if I consider Earth, then this corresponds to the north pole. That is angle theta, or the polar angle, and this phi basically is actually the values of theta and phi are actually the latitude and longitude, whichever way you define latitude. If I define polar angle as latitude, then azimuthal angle is the longitude. So with that understanding of the spherical polar coordinate system, we are now going to find the elemental area dA over here. So for that, what we are going to do is, we have considered, so now in this figure, theta is, this is the polar angle theta, and d theta was the small polar angle, small angle subtended by this elemental area dA, and our charge we are going to consider over at this area dA. So with respect to this angle theta, I can consider a triangle APQ. APQ triangle. No, and I can consider over here also an arc. Can consider an arc. So if I consider this angle over here and this d theta over here, then I can find the area if I know PQ and QR. So basically what you are going to do is, you are going to consider is like a rectangular area covered by this elemental area. So this I can give you as a task to shade over and try to find out the area with respect to this point A, or to the atom A. So I need the value of PQ and QR. PQ and QR. So I can get PQ if I do sine theta. So sine theta will be opposite side divided by the hypotenuse. So that means sine theta is PQ divided by R, or PQ becomes R into sine theta. In a similar way, I can do over here, or even consider this as an arc. So since the angle is small, sine of d theta will be d theta only. So once again, I'll get QR as R into d theta. So if I come over here, the total area, the metal area dA, if I am considering only the radial variable and the polar angle, then it is PQ into QR. But I also need to consider the azimuthal angle, and as we talked earlier, azimuthal angle varies from 0 to 2 pi. So I consider the maximum value of a symmetrical angle and take it as 2 pi. So total area dA, elemental area dA becomes 2 pi into PQ into QR. So let's substitute for PQ and QR. That's what we just got. So it's PQ is R sine theta and QR is R d theta. Resultant, you will get the elemental area dA as 2 pi into R square sine theta d theta. Now we go further. Why did we do all this? Is we need to find our aim is to find the electric field being generated by those charges at that spherical cavity. So first we have considered this small elemental area dA, and if there is a charge dq, sorry about that. If I consider the charge dq which is placed at that elemental area dA, then I can write dq is a product of the surface charge density and this elemental area. So it becomes sigma into dA. Now these are polarized charges, so we know that sigma can also be represented, or it is also equivalent to the polarization P. So dq becomes polarization vector into the elemental area vector. Now next what we are going to do is we are going to resolve this vector into two components. So whenever we resolve vector into two components, we get a horizontal component and a normal component. So the horizontal components, that's P cos theta, horizontal component is P cos theta, and the perpendicular component is P sin theta. The perpendicular components will cancel, and what we get is only the P cos theta. The cos components cancel and we get only P cos theta. So resultant is dq is P cos theta into dA. So this P is actually the polarization, so you can even consider it as capital P. dq is P cos theta into dA, and dA we have just found it is 2 pi r square sin theta d theta. So if I substitute here, it becomes P cos theta into 2 pi r square sin theta d theta, or I just rewritten as 2 pi r square into P cos theta into sin theta into d theta. Now I do it further. If I need to find the electric field due to this charge dq, then I have to bring in the Coulombs law. So Coulombs law, if I apply, I'll get E4 was our field component. So dE4, since it is for a small charge, elemental charge dq in a small elemental area dA, so the field is given by dE4 is 1 by 4 pi epsilon 0 into dq by r square. Once again, dq is a vector, and we are going to resolve the vector into two cos and sine component, and the sine components will cancel and the only one dominant will be the cos component. So the relation becomes dE4 is equal to 1 by 4 pi epsilon naught. So we get dE4 is equal to 1 by 4 pi epsilon naught into dq cos theta by r square. And we bring back dq from the previous page, that is 2 pi r square P cos theta sin theta d theta. If you substitute that, you will get dE4, it gets simplifies to P by 2 epsilon naught into cos square theta into sin theta into d theta. Now to find the total field, as we said earlier, we need to integrate it throughout. So it goes from theta is equal to 0 to pi. Why am I considering 0 to pi? Because 0 to pi by 2 is for one direction, the upward direction, then there is a 0 to minus pi by 2 on the other direction. If I consider throughout, then it becomes 0 to pi. Theta varies from 0 to pi. So we are going to next integrate 0 to pi dE4, or substitute for dE4 0 to pi P by 2 epsilon naught cos square theta sin theta d theta. P by 2 epsilon naught is a constant, it doesn't depend on theta, so I can take it out. So it becomes integral cos square theta sine theta d theta. Now this integral can be simplified if you consider cos theta as x, then dx becomes minus sine theta into d theta. This d theta over here is very important, and obviously the minus sign. I bring it back, I even change the limits from theta, I bring it to x, so it becomes p by 2 epsilon naught. So we had theta is equal to 0, x becomes cos 0, that is plus 1. When theta is equal to pi, x becomes cos pi, that is minus 1. Cos square theta becomes x square, and sine theta d theta we have, that is actually minus of dx. And to get rid of the negative sign, I just flip the limits. So it becomes minus 1 to 1 x square dx. So there is a small mistake here. There should have been a minus sign to the dx. That has come in the next step anyway. So minus p by 2 epsilon naught x cubed by 3. Right now the limit is 1 to minus 1. Either you can do it in this way, or you can interchange the limits and get rid of the minus. And finally you will end up getting p by 3 epsilon naught. So now the total electric field I can write as E1, that is due to free charges, E2 due to the bound charges at the sides of the dielectric, E3 was a contribution due to the neighboring atoms, which we found was negligible, and E4 is the value which we just found, that is at the charges at the spherical cavity. If I substitute everything, that is E plus p by epsilon naught is E1, E2 is minus p by epsilon naught, E3 is 0, and E4 is p by 3 epsilon naught. If I substitute everything, I will get the internal field as E plus p by 3 epsilon naught. So E was the applied field and p is a polarization vector. So the total internal field in a cubic solid is given by E internal, or EI, or is equal to E plus p by 3 epsilon naught. It's also called as Lorentz field or local field. So sometimes we write it as EI or E internal or E local or E Lorentz. So basically the important expression which you need to remember here is that the internal field is sum of applied field E plus polarization P divided by 3 epsilon naught, where epsilon naught is the permittivity of free space. So next we are going to make use of this expression for internal field or local field or Lorentz field, which we have just got, and let's consider that it's a particular dielectric where only the electronic polarization is dominant. We are going to consider that ionic and orientation polarizations are negligible. So if it is electronic polarization, we know this expression that polarization P is alpha E into N into the electric field. So instead of electric field, I am going to replace it with internal field, EI. So P is equal to alpha E into N into EI. Or alpha E, the polarizability, can be written as P divided by N into EI. And we just now got our expression for internal field, that was E plus P by 3 epsilon naught. If I substitute into this expression for polarizability, I am going to get alpha E is equal to P divided by N into E plus P by 3 epsilon naught. Now, in order to simplify this further, we are going to consider this relation which we have learned in the first lecture, that is polarization is directly proportional to electric field. We had got P is equal to chi epsilon naught E, or in another way chi is epsilon r minus 1, so it becomes P is equal to epsilon naught into epsilon r minus 1 into E. So what is epsilon r? Epsilon r is the dielectric constant or the relative permittivity. Now let's substitute for E from this particular expression. So we are going to replace for electric field E from this particular expression. So what do I get E here? I get as P divided by epsilon naught into epsilon r minus 1. Bringing it back into the expression for electronic polarizability, now it becomes alpha E is equal to P divided by N. I opened a big bracket over here, big square brackets. So Instead of E, I am going to write as P by epsilon naught into epsilon r minus 1 plus the P by 3 epsilon 0 remains as it is. Now the next job is to simplify this and get a relation. So what we are going to do is I just bring this n, it's 1 over n on the right hand side, when if it goes to the left hand side, n becomes in the, it gets multiplied and becomes in the numerator. So it becomes n alpha E is P divided by, and in the denominator, since P is common, I am taking out P. So it becomes P divided by P and whole brackets 1 by epsilon naught into epsilon r minus 1 plus P divided by 3 epsilon naught. Come to the next step. Oh, sorry, there is a mistake here. This should be 1. So we are basically taking out this factor P from the denominator. So it becomes P here, and 1 by epsilon naught into epsilon r minus 1 plus 1 by 3 epsilon naught. So P and P gets cancelled. So on the right hand side, I can see that it becomes 1 divided by 1 by epsilon naught into epsilon r minus 1 plus 1 by 3 epsilon naught. Again, epsilon naught is common, so I can take it out. So it becomes 1 divided by 1 whole divided by 1 by epsilon naught common into 1 by epsilon r minus 1 plus 1 divided by 3. Sorry, that's a message from a JRF. I need to pause it. Okay. So the next step is 1 divided by 1 by epsilon naught, that is basically epsilon naught. So epsilon naught becomes in the numerator. So epsilon naught divided by 1 by epsilon r minus 1 plus 1 by 3. Next, you are going to simplify this denominator, and also I am moving this epsilon naught to the left hand side. And in the next step, I do a rearrangement. And I get n alpha E by epsilon naught is 3 into epsilon r minus 1 by epsilon r plus 2. Bring 3 to the left hand side, it becomes n alpha E by 3 epsilon naught is equal to epsilon r minus 1 by epsilon r plus 2. And this is the Clausius-Mossotti equation or Clausius-Mossotti relation, which is applicable for non-polar solids with cubic crystal structure.